Okay, so we went over this question on Friday, but this was part of the overall sort of reaction mechanisms in chapter 3. So what's A? Reactants. B. Transition state. C. B. D. F. E. And the delta H in this reaction is the reaction is endo or exo? Exo, okay. Right? Everybody okay with all that? So then the next question is dealing with, there's two ways to cleave bonds in mechanisms. This was the first one. So when we're going to cleave the carbon-chlorine bond, I need to put one or multiple arrows here to show how the electrons are moving. And let's see what we got as an answer. All right, we got, most people put B, that single arrow. So why?
The electrons are moving from within the covalent bond over to chloride because it's got a negative charge and it would have been sharing an electron into the beginning and now it has an extra one.
Okay, so when I'm cleaving this bond, the fact that I'm getting a C plus and a Cl minus means that the carbon has lost an electron and the chlorine is gained, so that means both of these electrons are given to the chlorine. So I just need one arrow, and the arrow that I need is a full-headed arrow, which indicates a pair of electrons are moving. And they always move in the order in which the electrons are going, so they always move towards the negative. In the carbon-chlorine bond, the carbon's delta positive and the chlorine's delta negative. So the most electronegative element will always get the electrons. If the elements don't have an electronegativity difference, then you're not going to transfer a pair of electrons, you're just going to split them equally. So that's called heterolytic bond cleavage. Okay, and for the last one, if I wanted to form a bond from two species with unpaired electrons, what arrows am I going to use to show that? And looks like the majority said A. So each element or each atom is going to give up one electron. They're going to share it with the other. That means that I need to donate an electron from the chlorine, an electron from the carbon, and a half arrow is what we use to indicate that one electron is moving. Okay. All right. Any questions on any of those three? So I'm going to try and do is to come up with a few questions that we can use at the beginning of class here to go with whatever you would have. And so in chapter 3, we're talking about mechanisms. And now what we need to do is talk about some specific mechanisms and put some transition states and intermediates, real ones, together. All right, do you have any questions about chapter 3 stuff? Then let's start with looking at a couple of mechanisms. In your book, they talk about one-step and two-step mechanisms. And that's what I'm going to do, but I'm going to use reactions that we're going to learn here in a couple of weeks, or this is kind of setting the table for those. So the first thing that I'm going to do is I'm going to take something like ethyl chloride and I'm going to react it with a hydroxide ion. And I'm going to end up with ethanol and a chloride ion. So my first question to you is, what kind of reaction is that? Substitution. Do we agree it's a substitution reaction? Yes? So this is substitution. And it has a very specific name. So in organic chemistry, when we have species like the OH that are electron rich and have a negative charge, that's an indication that they are electron rich. Or if we have a chloride ion, which is also electron rich, the Lewis dot structure would have 8 electrons with a negative charge. These are called nucleophiles. And they're called nucleophiles because they're electron rich. So electron richness is either because you have a negative charge, which is a result of having lone pairs. That's where the electron richness comes from. We'll talk about neutral nucleophiles later on. So these are nucleophiles, which actually makes this reaction what's called an SN reaction. It's substitution nucleophilic, because I'm substituting one nucleophile for another. So when I substitute a nucleophile, it makes another one. Okay. Now, the opposite of nucleophiles are things called electrophiles. And electrophiles are electron poor. And they can be atoms that have either a delta positive or a full-blown positive 1 charge. Those are the electrophiles. Now, if you take the meaning of these two words, nucleophile means positive loving, electrophile means negative loving, they are opposites. Now, back in general chemistry, we might have called these things Lewis acids and Lewis bases, right? Because the donation of electrons was Lewis acid base acidity. But in organic, we tend not to use that term. We tend to use nucleophiles and electrophiles. That's just historically how it's been. So in the chemistry world, the electron rich always give to the electron poor. And if an electron rich species has the opportunity to give to 2 levels of electron poorness, they always give to the most poor. Okay, it's completely philanthropic. Electron rich don't give to other electron rich, and electron poor don't have anything to give to each other. Okay, you can compare that to real life if you want to see the difference, but chemistry is totally philanthropic. If you're rich, you got to give to the poor, and the poorest. Okay, and we'll leave it at that. So, this is a nucleophilic substitution reaction. This carbon on the chlorine, attached to the chlorine, of course, it's slightly positive because the chlorine carbon bond is polar covalent. So that's where the electrophile is. So when people first notice this reaction, they want to figure out what the mechanism is. And usually the way we start with a mechanism is we say, okay, let's do some kinetics on it. So we have to go back to general chemistry or beyond or further back and remember some basic things about kinetics. The first thing is I need to know what is the overall rate equation for this reaction. And so the most straightforward way of doing that is to say, okay, I'm going to double the concentration of the halide. I'm going to double the concentration of the hydroxide and see what the effects on the rates are. Right, so when I double the concentration on the alkyl halide, I get double the rate. And if I double the concentration of the hydroxide, I get double the rate. So you may remember back in general chemistry how you would have a table of different concentrations with different rates, and you would say, okay, here I kept this concentration the same, but I doubled this one. What happened to the rate? And so that's what they found, was that for this reaction, you double the rate, double the concentration of either species, you would double the rate. Double the concentration of both of them, and the rate would go up 4 times. So now we have enough data to write a rate equation. The rate equation being rate equals K times concentration, and I'm going to substitute just Rx for the alkyl halide, and then concentration of the hydroxide. And the exponents here should be 1 and 1, because if we double the rate, or double the reaction concentration, we double the rate. Right? If the exponents were 2, if I doubled the rate, what would happen to or if I doubled the concentration, the rate would go up by 2 squared or 4. Okay? So here's the overall rate equation. And in general chemistry, when I teach it, which is about once every 10 years at this point, I really stress the idea that this has to come from experiment. This did not, and notice the word not, come from stoichiometry. The overall rate equation always comes from experiment. So this is what we find for this reaction. And so now we can apply some terms here. For instance, this reaction is first order in alkyl halide. It is first order in hydroxide. And what rate is it, or what order is it overall? Second order? Because when you add the 2 orders together, you get the overall rate. So overall, this is second order. Now, that's going to tell me a little bit about the mechanism. Right. So everybody with me so far? So now what I'm going to do is now I really want to know what's the mechanistic steps for this reaction? Step by step, what happens? And so probably the easiest thing to do is let's take the simplest mechanistic step. The simplest mechanistic step that I always call this an elementary step, is that the hydroxide donates its pair of electrons to the carbon, so I'll use a full arrow for that. And of course, if that happens, that carbon's going to get 10 electrons unless what else happens? The carbon-chlorine bond breaks. So at the same time I'm forming my OH carbon bond, or my O carbon bond, I'm breaking my carbon-chlorine bond. And then on the other side, I will get the oxygen attached to carbon and a Cl minus. So that would be the simplest elementary step that I could show for this mechanism, or that I could propose for this mechanism. Now, for elementary steps, you are allowed to write the rate equation with stoichiometry as the rate orders. But that's only for elementary steps. So if I wanted to write the rate equation of this elementary step, I could simply say, oh, well, the rate equals concentration of the alkyl halide. There's one molecule of that times the concentration of hydroxide, and there's one molecule of that. So only with the elementary steps are you allowed to use stoichiometry. You're not with the overall one. And why is this important? Okay, that was a long silence, so I guess it's a rhetorical question. Why is this important? Because to determine what the mechanistic step is, it has to have the same rate equation as the overall rate equation. And technically, the rate equation that has the same, the mechanistic step that has the same rate equation as the overall rate equation is what we would call the rate determining step, the slow step if I have more than one. But in this case, I'm proposing a one-step mechanism, the simplest one I can propose. Does it have the same rate equation? Yes. Does that make it the absolute correct mechanistic step? Not necessarily, but given that there's probably 100 years in between when somebody did this and what we know now, this is the one individual mechanistic step. So this is the mechanistic step for this reaction, and it has the same rate equation as the overall reaction. Okay. All right, everybody with me? Still? Yes, no? I really shouldn't ask that. I should ask a question that makes you demonstrate that you're still with me. But we'll come to that. Okay. So this reaction could be thought of as a something molecular reaction. Since this involves the reaction of two molecules, this would be called a bimolecular reaction. It would also be bimolecular because we've got basically a second order rate equation. So this reaction then is what we would call an Sn2 mechanism, because the two standing for bimolecular. So this is nucleophilic substitution that is bimolecular, or what we'll call later on an Sn2 mechanism.
Wait, so you said it's also bimolecular because it's the second order reaction?
Yes,
So
in the
third order would be
trimolecular. And if it was one molecule with only one or first order, it would be unimolecular. So the molecularity of the reaction is how many molecules are colliding in that step, the slowest step of the mechanism. This only has one step. So we'll have to have multiple steps in the next one. Okay. Now, since there's only one step, there's one transition state. How many intermediates? Zero intermediates. Because in order for there to be an intermediate, you have to have more than one step. Because an intermediate is something that's produced in one step, one mechanistic step, as the product and then used as a reactant in a second step so that it cancels out and doesn't show up in the overall reaction. That's what an intermediate is. So this reaction has one transition state, no intermediate. So in terms of its reaction coordinate diagram, we would have one single transition state. So what does that look like? Well, how about a definition of what a transition state is? A transition state is a peak on the energy coordinate diagram. It is also a high energy species, which is why it's at the top of the energy coordinate diagram. You cannot put a transition state in a bottle and study it. It's too high energy. It exists for just a split second as the reaction occurs. So transition states have to be studied. A lot of times we can study them on the computer, or we can infer a lot of things. But I can't study a transition state directly. I can't do that. Transition states are also where you're making and breaking bonds. And it could be either. It could be making, could be breaking, or it could be both. So in this reaction, our transition state's going to look like this. We're going to have a partial bond between the oxygen and the carbon and the chlorine, because the two bonds I'm forming are an OC and breaking a CCl. And from other evidence that we'll talk about later, the oxygen has to be in line with the chlorine. The other three groups actually make that transition state have a trigonal bipyramidal geometry. So this species is the transition state. Now, when we write a transition state, we use dotted lines to indicate the bonds that are being broken or formed. So I'm breaking a CCl bond, I'm forming an OH bond. We also need to put charges in. So the charge on the oxygen is, it's going from -1 to 0 in terms of its formal charge. So that means its average is delta minus. So I'm going to determine the transition state, bonds, and the charges the same way I determine the resonance hybrid, by taking an average of bonds and an average of charges. That means chlorine is going from going 0 to -1, therefore the chlorine should be delta minus. And if we saw this reaction, if we could see it sort of as an animation, the oxygen is transferring its electron density to the chlorine as it leaves. What's also happening is that the carbon is tetrahedral, but as the oxygen approaches the carbon, the bonds that are bent like this are going to flatten out, and then they're going to flip to the other side once the chlorine leaves. And we'll get into that. That's called inversion of configuration later on, but we need to know what a configuration is before we talk about inverting it. Okay. So in the middle, the bonds are perfectly in between the other groups, and then the O and the Cl. So this is the transition state for that reaction.
Shouldn't carbon only have 4 bonds, so why does it have 5?
Well, that's a good question. So before you say, hey, you're violating the octet rule, which I am not, there's only 4 bonds. There's only 4 total bonds here. The dotted lines are partial bonds. And so they basically add up to one bond. So I didn't form 5 bonds to a carbon. And even if I did, this is a high energy species. Now you can't violate the 5 bond rule in a high energy species either, but we basically have 3 and then 2 partial bonds. Okay. So there's our transition state. And we know more about that transition state because later on we'll talk about, later on meaning later on in a couple weeks, we'll talk about inversion of configuration, which is the key evidence that this backside attack of the nucleophile on the carbon is the mechanism. Okay. Right. So everybody, that's the mechanism. That's a one-step nucleophilic substitution mechanism. And in order to prove that, you would want to try some different parameters in this reaction to see if they make sense with that overall reaction. For instance, since the OH minus has to attack the carbon, the smaller the groups around the carbon, the faster the reaction is going to be. If I make these groups too large, the O minus can't get to the carbon, and so the reaction can't occur. So that might be one piece of evidence that I put to this and say, okay, that proves this mechanism, which you can never really do. You can only just try and keep disproving the reaction until you're done and then it's accepted, until somebody comes along and disproves it. So mechanisms are like accepted, but they're never completely 100% true. Unless they make it in or like a textbook, then they're probably true. Because nobody has busted them up for 100 years. But if somebody comes up with a new mechanism, there are tons of people out there that are going to try and break that mechanism. And so if it stands, it's good. If it doesn't, new mechanism. Okay. So this is bimolecular substitution. Everybody okay? So, one question. Is that carbon primary, secondary, or tertiary? The one I just circled. The one with the chlorine. That one. Primary, secondary, or tertiary? Here, we'll do the finger thing. Primary, secondary, tertiary. Primary, the first finger only, please. So, on 3, what is it? Is it primary, secondary, or tertiary? Well, you never know. All right. 1, 2, 3. Oh, we're all over the place. It's 1. That's a primary carbon. What? Because it's only bonded to one carbon. So it's primary. So primary, secondary, and tertiary carbons, you determine those by the number of carbons that they're attached to. Chlorine doesn't count. Only carbon. So this is a primary alkyl halide. Okay. So now, maybe the same person, maybe somebody else, they decided to change the alkyl halide and do the reaction with hydroxide. They're going to do the same substitution reaction. So they're substituting the OH with the Cl. Okay. Got to ask this question. The carbon, well, I'd say the name of this, but that would give it away. That carbon that I just circled, what kind of carbon is it? Primary, secondary, or tertiary? Because that molecule is, right, it's tertiary butyl chloride would be its common name. Naming the alkyl group followed by the halogen. So that's tertiary butyl chloride. Okay, so that's a tertiary carbon. So somebody goes and they do this reaction, and they find out that when they double the concentration of the alkyl halide, the reaction rate doubled. And then when they doubled the concentration of the hydroxide, the rate stayed the same. The rate didn't change. Then they tripled the concentration and the rate still didn't change. Then they went back and repeated it, and they probably had somebody else repeat it. And so it has different kinetics. And when you find out a reaction has two different kinetics, that means that it probably has different mechanisms. Not probably, it does. So this has a different mechanism than the primary one. I mean, I don't know who did this because this reaction doesn't have a name associated with it, like most organic reactions do. But whoever found this out, or whenever they did this, that must have been a pretty cool reaction. Because it's like, oh wait, this completely changed. And then they go back and do it again and get somebody else to do it, and it's like, oh, well, you need to figure out what this mechanism is. Okay, so let's do that. So in this case, we have to propose a new mechanism because the alkyl halide reacting with the hydroxide in one step, that's a bimolecular reaction. This one, the rate equals K times the concentration of the alkyl halide to the first power times the concentration of the hydroxide to the zero power. Because everything to the zero power is 1. So it doesn't exist. So we have to come up with a mechanism whose rate equation is exactly the overall rate equation. And so what they decided was, okay, let's take this tertiary butyl chloride, and in the first step, how about I break the carbon-chlorine bond with our full-headed arrow and form a plus charge and a chloride.
Why would that bond break in the first place?
Well, there has to be something that drives it. So none of these reactions are in the gas phase, meaning these aren't isolated molecules. These are in solution. So if you think about doing this in solution, maybe the solvation of the chloride ion and the solvation of the C plus ion is enough to stabilize the breaking of that bond. Is it going to cost me energy? Yeah. Am I going to get more energy out? Maybe. That's Wednesdays. Wednesday we're going to talk about free energy, right? Because is a reaction spontaneous? It depends on the delta H and the entropy term, the disorder term. Forming two molecules out of one, that's an increase in disorder, which is what That's the what? Second law of thermodynamics? I think the first one's you can't create or destroy energy, and then the second one is that the world likes, well, it likes disorder. Everything moves towards disorder, which, yeah, kind of makes sense. Outside of organic chemistry as well as inside. So we've got disorder going for us. So that's why it would happen. Most likely you have a solvation. If I'm going to make this happen, just as an aside, if you add like silver ion to the solution, once the silver will basically pull the chloride off and precipitate. So you can pair up the chloride once it's dissociated and really make this happen. So if you want to know if this happened, you could take the alkyl halide, add a little silver to it, see it precipitate, you just formed the carbocation. If you didn't see that, or if it happened over a long time, you could see what the relative rate of the reaction is. That's how it was done originally, or how we can do it and visually see this. So there's my step number one. Then, once I form this C+ species, my hydroxide being a nucleophile and my C+ being an electrophile, the OH will come in, donate a pair of electrons to the plus charge, and I will make my product. So what I've now proposed are two elementary steps, elementary step number 1 and elementary step number 2. And now I can write the rate equations. The rate equation for the first step is rate equals concentration of the alkyl halide to the first power, because that's all the reactants there are. The rate equation for the second reaction is going to involve some substitution, because you'd have the rate of the hydroxide concentration times the rate of the C+ species, and then you'd have to say, well, where did the C+ species come from? The C+ species came from the alkyl halide. So, except for me as the expert in the classroom, that this second step would be bimolecular. And it already is bimolecular. It's got 2 molecules. So that's what we're really looking at. So guess what? The rate of the first step equals the overall rate of the equation, the overall rate equation. So what does that mean? It means that's the slow step, or that's the rate determining step of the reaction. So that's the rate determining step. So whenever you have multiple steps, they will occur at different rates. The slow step is the rate determining step. That dictates how fast the product's formed. It takes a long time for the chloride to break. As soon as the chloride breaks, hydroxide comes right in and adds to it. So the first step's the rate determining step. Okay. So somebody proposed this. My rates are the same. My rate equations are the same. So, now comes the difficult part. Can I observe a carbocation? Can I observe that in solution? It depends on the carbocation. There are some that you could put in a bottle for a long time. There are some that are going to be relatively unstable. So, and people spent most of the 60s looking at different types of carbocations. And they just got stranger and stranger and stranger as they went along. we're going to find out that a carbocation has to be flat. The carbons that are attached to the C+, it has to be a trigonal planar geometry. And remember our friends, the bicyclics? Somebody put a chlorine or a fluorine there on the bridgehead, and the bridgehead can't be flat. It can never be flat. So they went about trying to make a carbocation at that position, and they never could. So that's how extensive the experiments went. They tried to make a non-planar carbocation, and they couldn't. And I know because there was a compound similar to this that I found in my graduate lab. It was sitting in the back corner, and I did a bottle. I opened it up. There was a nice letter in there from a Nobel laureate, and I should have kept it. But there's the letter, and he's talking to my boss, and he said, "Hey, Ned, this is the world supply of this compound. Can you test it for the non-traditional carbocations and then send it back to me?" Well, this was like 20 years after the fact, so it never got sent back to him. But I don't think it ever formed a carbocation either. So it was one of these molecules where they put a halogen on a bridgehead. So people spent a lot of time looking for the characteristics of carbocations. Because when you have an intermediate, you need to prove that it exists. But more importantly, you need to prove what you need to show what its characteristics are. And we'll look at one characteristic here, which is, first of all, what is this species? In the mechanism, that would be called an it was on the original reaction coordinate diagram that I gave you at the beginning of class. That is an intermediate. Why? Because it's produced in one step and react or consumed in the second step. So that's an intermediate. The more evidence you can have about intermediates, the more that likely people will accept what you're saying. So the first thing is, any carbon with a plus charge only has 6 electrons. So how can I make it stable? Last thing, we'll end with this. Anytime you add an alkyl group to a C+, it stabilizes it. Because what happens is that the hydrogen is slightly less electronegative than carbon. So the carbon picks up some electron density from the hydrogens, and it's able to share or push a little bit of that electron density in that carbon. Now, that carbon's got 6 electrons. It may end with something like 6.2. But every alkyl group you can give that C+ is going to make it more stable. So a tertiary carbocation is going to be more stable than a secondary carbocation, which will be far more stable than a primary, because in my rules of organic chemistry, number 1, don't take the class unless you have to. Number 2, no 5 bonds to the carbon. And number 3, no primary carbocations this semester. Next semester, we're going to talk about a technique called mass spectrometry, which is in the high energy gas phase. That rule doesn't apply. But in solution, no primary carbocations. Okay. So on Wednesday, we'll finish this SN1 reaction. Talk about a little bit about Hammond's postulate, and then finish up the material in chapter 3. Okay. If you have questions, email me. Otherwise, we'll finish this up and finish up chapter 3 on Wednesday.